Piping vibration, high-frequency acoustic excitation, understanding vibration effects caused by acoustic waves. Introduction to high-frequency acoustic excitation, overview and significance. High-frequency acoustic excitation is a critical phenomenon in process piping systems, particularly in gas services where pressure-reducing devices are present. Unlike low-frequency vibration mechanisms, this excitation occurs at frequencies typically between 500 Hz and 2000 Hz, which can rapidly induce fatigue failures in piping components. The significance of this mechanism lies in its ability to generate severe dynamic stresses in a very short time frame, often leading to failures within hours of operation. Acoustic excitation is associated with high-energy pressure fluctuations and shock waves that propagate through the piping system, exciting shell flexural modes of the pipe wall. These modes are highly localized and affect circumferential discontinuities such as small bore connections, welded supports, and fabricated tees. Understanding this phenomenon is essential for engineers because it directly impacts safety-critical systems like relief and blowdown lines, where failure can result in catastrophic consequences including hazardous fluid release, environmental damage, and operational downtime. The design codes often provide limited guidance on acoustic fatigue, making awareness and proactive design strategies vital for mitigating risks. Mechanism of acoustic energy generation. How acoustic excitation occurs. Acoustic energy in piping systems is generated primarily by high-pressure drops across control valves, relief valves, or orifice plates. When gas flows through these devices, it experiences rapid acceleration and deceleration, creating turbulence and shock waves downstream of the restriction. In cases of choked flow, where the gas velocity reaches sonic conditions, the intensity of acoustic energy increases dramatically. The interaction of high-velocity jets with the pipe wall and the mixing of turbulent streams produce strong pressure oscillations that propagate as acoustic waves. These waves excite the pipe wall at its natural shell modes, resulting in localized flexural vibration. Unlike broadband turbulence, acoustic excitation is tonal, meaning energy is concentrated at specific frequencies determined by the geometry of the restriction and flow conditions. The dominant frequencies typically fall within the range of 500 to 2000 Hz, which corresponds to the natural frequencies of thin-walled piping components. This coupling between acoustic energy and structural response leads to high dynamic stresses at welds and discontinuities, accelerating fatigue damage. Sources of high-frequency acoustic excitation, pressure-reducing devices and flow restrictions. The most common sources of high-frequency acoustic excitation in process piping systems are pressure-reducing devices such as control valves, relief valves, and orifice plates. These components create abrupt changes in flow velocity and pressure, which generate intense acoustic energy. Control valves operating under high differential pressure conditions are particularly prone to producing strong acoustic waves, especially when fitted with standard trims that allow high jet velocities. Relief valves and blowdown valves, which open rapidly during emergency depressurization, can also induce severe acoustic excitation due to the sudden release of high-pressure gas. Orifice plates, used for flow measurement or pressure control, contribute to this phenomenon by creating localized turbulence and shock waves downstream. The severity of acoustic excitation depends on factors such as pressure drop magnitude, gas density, mass flow rate, and whether the flow reaches sonic conditions. Systems designed without consideration for these factors are at high risk of experiencing acoustic fatigue failures shortly after commissioning. Frequency range and vibration characteristics, dominant frequencies and structural response. High-frequency acoustic excitation typically occurs within the range of 500 Hz to 2000 Hz. These frequencies correspond to the shell flexural modes of the pipe wall, which involve localized bending of the pipe circumference rather than global displacement of the entire pipe span. Because these modes are highly localized, visual observation of vibration is often impossible, making detection challenging without specialized instrumentation. The dynamic stresses induced by these vibrations are concentrated at circumferential discontinuities such as small bore connections, welded supports, and fabricated tees. The amplitude of vibration may appear small, but the associated stress cycles are extremely high. leading to rapid fatigue crack initiation and propagation. Unlike low-frequency vibration, which may take months or years to cause damage, high-frequency acoustic excitation can result in failure within hours of exposure. This characteristic underscores the importance of predictive analysis and proactive design measures to prevent catastrophic failures in critical piping systems. Impact on piping integrity and safety, consequences of acoustic fatigue. The impact of high-frequency acoustic excitation on piping integrity is severe and often underestimated. The localized dynamic stresses generated by shell flexural modes can initiate fatigue cracks at weld toes and other stress concentrators within minutes of operation. Once initiated, these cracks propagate rapidly, leading to through-wall failures and loss of containment. Such failures are particularly dangerous in systems handling hazardous or flammable gases, as they can result in explosions, fires, and environmental contamination. Additionally, failures in relief or blowdown systems compromise the safety mechanisms designed to protect equipment from overpressure, creating a significant risk of catastrophic plant incidents. The short time to failure associated with acoustic fatigue means that traditional inspection and maintenance strategies are ineffective for prevention. Instead, proactive design measures and predictive analysis are essential to ensure system reliability and safety. Factors influencing acoustic excitation severity, key parameters, and their effects. Several factors influence the severity of high-frequency acoustic excitation in piping systems. The most critical parameters include the magnitude of pressure drop across the restriction, the gas mass flow rate, and the occurrence of choked flow conditions. A higher pressure drop increases the velocity of the gas jet, which in turn amplifies the acoustic energy generated. Similarly, higher mass flow rates contribute to greater turbulence and shock wave intensity downstream of the restriction. Choked flow, where the gas velocity reaches sonic conditions, represents the most severe case, as it produces strong shock waves and high levels of acoustic energy. Other contributing factors include the geometry of the pressure-reducing device, the presence of multiple restrictions in series, and the acoustic properties of the piping system, such as length and diameter. Understanding these parameters is essential for engineers to predict and mitigate acoustic fatigue risks during the design phase. Preventive measures and design best practices, strategies for mitigation. Preventing high-frequency acoustic excitation requires a combination of design modifications and operational strategies. One effective approach is the use of low-noise valve trims, such as multi-stage pressure drop designs, which reduce jet velocity and turbulence downstream of the valve. Increasing the distance between the pressure-reducing device and sensitive components can also help attenuate acoustic energy before it reaches critical locations. Reinforcing thin-walled sections and eliminating circumferential discontinuities, where possible, reduces susceptibility to fatigue. For unavoidable discontinuities, full wraparound reinforcement or the use of forged tees instead of fabricated ones can improve fatigue resistance. Additionally, predictive acoustic analysis using computational tools should be performed during the design phase to identify potential resonance conditions and optimize system layout. In some cases, installing acoustic silencers or diffusers may be considered, although their effectiveness and durability can vary. These measures, combined with adherence to industry best practices, significantly reduce the risk of acoustic fatigue failures. Guidelines for acoustic fatigue management. Industry standards provide limited but important guidance on managing acoustic fatigue in piping systems. While general piping codes such as ASME 31.3 do not explicitly address high-frequency acoustic excitation, specialized guidelines and recommended practices have been developed by organizations like the Energy Institute and API. API standards, including API 521 for pressure-relieving systems, emphasize the need to consider acoustic fatigue during design, particularly for relief and blowdown lines. The Energy Institute's guidelines offer detailed methodologies for assessing acoustic excitation risks and implementing corrective actions. These documents recommend predictive analysis, proper valve selection, and reinforcement of critical components as key strategies for mitigating acoustic fatigue. Compliance with these guidelines, combined with engineering judgment and advanced simulation techniques, ensures that piping systems are designed to withstand the severe dynamic stresses associated with high-frequency acoustic excitation.